Sampling fundamentals. 8. Sampling may be defined as the selection of some part of an aggregate or totality on the basis of which a judgment or inference about the aggregate or totality is made. In other words, it is the process of obtaining information about an entire population by examining only a part of it. In most of the research work and surveys, the usual approach happens to be to make generalizations or to draw inferences based on samples about the parameters of population from which the samples are taken. The researcher quite often selects only a few items from the universe for his study purposes. All this is done on the assumption that the sample data will enable him to estimate the population parameters. The item so selected constitutive hat is technically called a sample, their selection process or technique is called sample design, and the survey conducted on the basis of sample is described as sample. Survey. Sample should be truly representative of population characteristics without any bias so that it may result in valid and reliable conclusions. Need for sampling. Sampling is used in practice for a variety of reasons such as 1. Sampling can save time and money. A sample study is usually less expensive than a census study and produces results at a relatively faster speed. 2. Sampling may enable more accurate measurements for a sample study is generally conducted by trained and experienced investigators. 3. Sampling remains the only way when population contains infinitely many members. 4. Sampling remains the only choice when a test involves the destruction of the item under study. 5. Sampling usually enables to estimate the sampling errors and thus assists in obtaining information concerning some characteristic of the population. Some fundamental definitions. Before we talk about details and uses of sampling, it seems appropriate that we should be familiar with some fundamental definitions concerning sampling concepts and principles. 1. Universe population. From a statistical point of view, the term universe refers to the total of the items or units in any field of inquiry, whereas the term population refers to the total of items about which information is desired. The attributes that are the object of study are referred to as characteristics, and the units possessing them are called as elementary units. The aggregate of such units is generally described as population. Thus, all units in any field of inquiry constitute universe, and all elementary units, on the basis of one characteristic or more, constitute population. Quite often, we do not find any difference between population and universe, and as such the two terms are taken as interchangeable. However, a researcher must necessarily define these terms precisely. The population or universe can be finite or infinite. The population is said to be finite if it consists of a fixed number of elements so that it is possible to enumerate it in its totality. For instance, the population of a city, the number of workers in a factory are examples of finite populations. The symbol N is generally used to indicate how many elements or items are there in case of a finite population. An infinite population is that population in which it is theoretically impossible to observe all the elements. Thus, in an infinite population the number of items is infinite, i.e., we cannot have any idea about the total number of items. The number of stars in a sky, possible rolls of a pair of dice are examples of infinite population. One should remember that no truly infinite population of physical objects does actually exist, in spite of the fact that many such populations appear to be very, very large. From a practical consideration, we then use the term infinite population for a population that cannot be enumerated in a reasonable period of time. This way we use the theoretical concept of infinite population as an approximation of a very large finite population. 2. Sampling frame. The elementary units or the group or cluster of such units may form the basis of sampling process, in which case they are called a sampling units. A list containing all such sampling units is known as sampling frame. Thus, sampling frame consists of a list of items from which the sample is to be drawn. If the population is finite and the time frame is in the present or past, then it is possible for the frame to be identical with the population. In most cases they are not identical because it is often impossible to draw a sample directly from population. Such this frame is either constructed by a researcher for the purpose of his study or may consist of some existing list of the population. For instance, one can use telephone directory as a frame for conducting opinion survey in a city. Whatever the frame may be, it should be a good representative of the population. 3. Sampling design. A sample design is a definite plan for obtaining a sample from the sampling frame. It refers to the technique or the procedure the researcher would adopt in selecting some sampling units from which inferences about the population is drawn. Sampling design is determined before any data are collected. Various sampling designs have already been explained earlier in the book. 4. Statistics and parameters. A statistic is a characteristic of a sample, whereas a parameter is a characteristic of a population. Thus, when we work out certain measures such as mean, median, mode or like ones from samples, then they are called statistics, for they describe the characteristics of a sample. But when such measures describe the characteristics of a population, they are known as parameters. For instance, the population mean is a parameter, whereas the sample mean, x, is a statistic. To obtain the estimate of a parameter from a statistic constitutes the prime. Objective of sampling analysis. 5. Sampling error. Sample surveys do imply the study of a small portion of the population, and as such there would naturally be a certain amount of inaccuracy in the information collected. This inaccuracy may be termed as sampling error or error variance. In other words, sampling errors are those errors which arise on account of sampling, and they generally happen to be random variations, in case of random sampling, in the sample estimates around the true population values. The meaning of sampling error can be easily understood from the following diagram. Pause the video to look at the figure. Fig. 8.1. Sampling error is equal to frame error plus chance error plus response error. If we add measurement error or the non-sampling error to sampling error, we get total error. Sampling errors occur randomly and are equally likely to be in either direction. The magnitude of the sampling error depends upon the nature of the universe. The more homogeneous the universe, the smaller the sampling error. Sampling error is inversely related to the size of the sample, i.e., sampling error decreases as the sample size increases and vice versa. A measure of the random sampling error can be calculated for a given sample design and size, and this measure is often called the precision of the sampling plan. Sampling error is usually worked out as the product of the critical value at a certain level of significance and the standard error. As opposed to sampling errors, we may have non-sampling errors which may creep in during the process of collecting actual information, and such errors occur in all surveys, whether census or sample. We have no way to measure non-sampling errors. 6. Precision. Precision is the range within which the population average or other parameter will lie in accordance with the reliability specified in the confidence level as a percentage of the estimate or as a numerical quantity. For instance, if the estimate is 4,000 rupees and the precision desired is 4%, then the true value will be no less than 3,840 rupees and no more than 4,160 rupees. This is the range, 3,840 rupees to 4,160 rupees, within which the true answer should lie. But if we desire that the estimate should not deviate from the actual value by more than 200 rupees in either direction, in that case the range would be 3,800 rupees to 4,200 rupees. 7. Confidence level and significance level. The confidence level or reliability is the expected percentage of times that the actual value will fall within the stated precision limits. Thus, if we take a confidence level of 95%, then we mean that there are 95 chances in 100 or 0.95 in 1 that the sample results represent the true condition of the population within a specified precision range against 5 chances in 100 or 0.05 in 1 that it does not. Precision is the range within which the answer may vary and still be acceptable. Confidence level indicates the likelihood that the answer will fall within that range, and the significance level indicates the likelihood that the answer will fall outside that range. We can always remember that if the confidence level is 95%, then the significance level will be 100 to 95, i.e., 5%. If the confidence level is 99%, the significance level is 100 to 99, i.e., 1%, and so on. We should also remember that the area of normal curve within precision limits for the specified confidence level constitute the acceptance region, and the area of the curve outside these limits in either direction constitutes the rejection regions. 8. Sampling distribution. We are often concerned with sampling distribution in sampling analysis. If we take certain number of samples and for each sample compute various statistical measures such as mean, standard deviation, etc., then we can find that each sample may give its own value for the statistic under consideration. All such values of a particular statistic, say mean, together with their relative frequencies will constitute the sampling distribution of the particular statistic, say mean. Accordingly, we can have sampling distribution of mean, or the sampling distribution of standard deviation, or the sampling distribution of any other statistical measure. It may be noted that each item in a sampling distribution is a particular statistic of a sample. The sampling distribution tends quite closer to the normal distribution if the number of samples is large. The significance of sampling distribution follows from the fact that the mean of a sampling distribution is the same as the mean of the universe. Thus, the mean of the sampling distribution can be taken as the mean of the universe. Important sampling distributions. Some important sampling distributions, which are commonly used, are 1. Sampling distribution of mean, 2. Sampling distribution of proportion, 3. Students t-distribution, 4. F-distribution, and 5. Chi-square distribution. A brief mention of each one of these sampling distribution will be helpful. 1. Sampling distribution of mean. Sampling distribution of mean refers to the probability distribution of all the possible means of random samples of a given size that we take from a population. If samples are taken from a normal population, N, P, the sampling distribution of mean would also be normal with a mean X and standard deviation Pn, where is mean of population. P is the standard deviation of the population and N means the number of items in a sample. But when sampling is from a population which is not normal, may be positively or negatively skewed, even then, as per the central limit theorem, the sampling distribution of mean tends quite closer to the normal distribution, provided the number of sample items I large, i.e., more than 30. In case we want to reduce the sampling distribution of mean to unit normal distribution, i.e., n, 0, 1, we can write the x Pn PQN normal variate Z fourth sampling distribution of mean. This characteristic of sampling distribution of mean is very useful in several decision situations for accepting or rejection of hypotheses. 2. Sampling distribution of proportion. Like sampling distribution of mean, we can as well have a sampling distribution of proportion. This happens in case of statistics of attributes. Assume that we have worked out the proportion of defective parts in large number of samples, each with say 100 items, hath we been taken from an infinite population and plot a probability distribution of said proportions, we obtain what is known as the sampling distribution of the said proportions, we obtain what is known as the sampling distribution of proportion. Usually the statistics of attributes correspond to the conditions of a binomial distribution that tends to become normal distribution as n becomes larger and larger. If P represents the proportion of defectives, i.e., of successes, and Q the proportion of non-defectives, i.e., of failures, or Q is equal to 1 P, and if P is treated as a random variable, then the sampling distribution of proportion of successes has a mean is equal to P with standard deviation, where n is the sample size. Presuming the binomial distribution approximating the normal distribution for large n, the normal variate of sampling distribution of proportion ZPP, where P pronounced as P hat is the sample proportion of successes, can be used for testing of hypotheses. 3. Students' T distribution. When population standard deviation, T, is not known and the sample is of a small size, i.e., n30, we use T distribution for the sampling distribution of mean and work out T variable as T, where S, i.e., the sample standard deviation. T distribution is also symmetrical and is very close to the distribution of standard normal variate, Z, except for small values of n. The variable T differs from Z in the sense that we use sample standard deviation, S, in the calculation of T, whereas we use standard deviation of population, P, in the calculation of Z. There is a different T distribution for every possible sample size, i.e., for different degrees of freedom. The degrees of freedom for a sample of size n is n1. As the sample size gets larger, the shape of the T distribution becomes approximately equal to the normal distribution. In fact, for sample sizes of more than 30, the T distribution is so close to the normal distribution that we can use the normal to approximate the T distribution. But when n is small, the T distribution is far from normal, but when n, T distribution is identical with normal distribution. The T distribution tables are available which give the critical values of T for different degrees of freedom at various levels of significance. The table value of T for given degrees of freedom at A, PQN, SP. Certain level of significance is compared with the calculated value of T from the sample data, and if the latter is either equal to or exceeds, we infer that the null hypothesis cannot be accepted. F cent. F distributive. On Pause the video to read this paragraph H. F ratio is computed in a way that the larger variance is always in the numerator. Tables have been prepared for F distribution that give critical values of F for various values of degrees of freedom for larger as well as smaller variances. The calculated value of F from the sample data is compared with the corresponding table value of F, and if the former is equal to or exceeds the latter, then we infer that the null hypothesis of the variances being equal cannot be accepted. We shall make use of the F ratio in the context of hypothesis testing and also in the context of ANOVA technique. 4. Chi-square 2. Distribution. Chi-square distribution is encountered when we deal with collections of values that involve adding up squares. Variances of samples require us to add a collection of squared quantities and thus have distributions that are related to chi-square distribution. If we take each one of a collection of sample variances, divide them by the known population variance and multiply these quotients by n1, where n means number of items in the sample, we shall obtain a chi-square distribution. Thus, 2 n1 would have the same distribution as chi-square distribution with n1 degrees of freedom. Chi-square distribution is not symmetrical and all the values are positive. One must know the degrees of freedom for using chi-square distribution. This distribution may also be used for judging the significance of difference between observed and expected frequencies and also as a test of goodness of fit. The generalized shape of 2 distribution depends upon the df and the 2 value is worked out as underscore. Tables are there that give the value of 2 for given df, which may be used with calculated value of 2 for relevant df at a desired level of significance for testing hypotheses. We will take it up in detail in the chapter chi-square test. Central limit theorem. When sampling is from a normal population, the means of samples drawn from such a population are themselves normally distributed. But when sampling is not from a normal population, the size of the sample plays a critical role. When n is small, the shape of the distribution will depend largely on the shape of the parent population, but as n gets large, n30, the thape of the sampling distribution will become more and more like a normal distribution, irrespective of the shape of the parent population. The theorem which explains the sort of relationship between the shape of the population distribution and the sampling distribution of the mean is known as the central limit theorem. This theorem is by far the most important theorem in statistical inference. It assures that the sampling distribution of the mean approaches normal distribution as the sample size increases. In formal terms, we may say that the central limit theorem states that the distribution of means of random samples taken from a population having mean and finite variance to approaches normal distribution with mean and variance to n as n goes to infinity. The significance of the central limit theorem lies in the fact that it permits us to use sample statistics to make inferences about population parameters without knowing anything about the shape of the frequency distribution of that population other than what we can get from the sample. Sampling theory. Sampling theory is a study of relationships existing between a population and samples drawn from the population. Sampling theory is applicable only to random samples. For this purpose, the population or a universe may be defined as an aggregate of items possessing a common trait or traits. In other words, A universe is the complete group of items about which knowledge is sought. The universe may be finite or infinite. Finite universe is one which has a definite and certain number of items, but when the number of items is uncertain and infinite, the universe is said to be an infinite universe. Similarly, the universe may be hypothetical or existent. In the former case, the universe in fact does not exist, and we can only imagine the items constituting it. Tossing of a coin or throwing a dice are examples of hypothetical universe. Existent universe is a universe of concrete objects, i.e., the universe you hear the items constituting it really exist. On the other hand, the term sample refers to that part of the universe which is selected for the purpose of investigation. The theory of sampling studies the relationships that exist between the universe and the sample or samples drawn from it. The main problem of sampling theory is the problem of relationship between a parameter and a statistic. The theory of sampling is concerned with estimating the properties of the population from those of the sample and also with gauging the precision of the estimate. This sort of movement from particular sample towards general universe is what is known as statistical induction or statistical inference. In more clear terms, from the sample we attempt to draw inference concerning the universe. In order to be able to follow this inductive method, we first follow a deductive argument, which is that we imagine a population or universe, finite or infinite, and investigate the behavior of the samples drawn from this universe applying the laws of probability. The methodology dealing with all theses known as sampling theory. Sampling theory is designed to attain one or more of the following objectives. NPQ I. Statistical estimation. Sampling theory helps in estimating unknown population parameters from a knowledge of statistical measures based on sample studies. In other words, to obtain an estimate of parameter from statistic is the main objective of the sampling theory. The estimate can either be a point estimate or it may be an interval estimate. Point estimate is a single estimate expressed in the form of a single figure, but interval estimate has two limits with the upper limit and the lower limit within which the parameter value may lie. Interval estimates are often used in statistical induction. 2. Testing of hypotheses. The second objective of sampling theory is to enable us to decide whether to accept or reject hypotheses. The sampling theory helps in determining whether observed differences are actually due to chance or whether they are really significant. 3. Statistical inference. Sampling theory helps in making generalization about the population universe from the studies based on samples drawn from it. It also helps in determining the accuracy of such generalizations. The theory of sampling can be studied under two heads, viz., the sampling of attributes and the sampling of variables, and that too in the context of large and small samples. By small sample is commonly understood any sample that includes 30 or fewer items, whereas a large sample is one in which the number of items is more than 30. When we study some qualitative characteristic of the items in a population, we obtain statistics of attributes in the form of two classes, one class consisting of items wherein the attribute is present and the other class consisting of items wherein the attribute is absent. The presence of an attribute may be termed as a success and its absence a failure. Thus, if out of 600 people selected randomly for the sample, 120 are found to possess a certain attribute and 480 are such people where the attribute is absent. In such a situation, we would say that sample consists of 600 items, i.e., n is equal to 600. out of which 120 are successes and 480 failures. The probability of success would be taken as 120 by 600 is equal to 0.2, i.e., p is equal to 0.2, and the probability of failure or q is equal to 480 by 600 is equal to 0.8. With such data, the sampling distribution generally takes the form of binomial probability distribution whose mean would be equal to NP and standard deviation T would be equal to .ifn I large. The binomial distribution tends to become a normal distribution, which may be used for sampling analysis. We generally consider the following three types of problems in case of sampling of attributes. I. The parameter value may be given, and it is only to be tested if an observed statistic is its estimate. 2. The parameter value is not known, and we have to estimate it from the sample. 3. Examination of the reliability of the estimate, i.e., the problem of finding out how far the estimate is expected to deviate from the true value for the population. All the above stated problems are studied using the appropriate standard errors and the tests of significance, which have been explained and illustrated in the pages that follow. The theory of sampling can be applied in the context of statistics of variables, i.e., data relating to some characteristic concerning population which can be measured or enumerated with the help of some well-defined statistical unit, in which case the objective happens to be I, to compare the observed and expected values and to find if the difference can be ascribed to the fluctuations of sampling, 2, to estimate population parameters from the sample, and 3, to find out the degree of reliability of the estimate. The tests of significance used for dealing with problems relating to large samples are different from those used for small samples. This is so because the assumptions we make in case of large samples do not hold good for small samples. In case of large samples, we assume that the sampling distribution tends to be normal and the sample values are approximately close to the population values. As such, we use the characteristics of normal distribution and apply what is known as z-test. When n is large, the probability of a sample value of the statistic deviating from the parameter by more than 3 times its standard error is very small. It is 0.0027 as per the table giving area under normal curve, and as such the z-test is applied to find out the degree of reliability of a statistic in case of large samples. Appropriate standard errors have to be worked out which will enable us to give the limits within which the parameter values would lie or would enable us to judge whether difference happens to be significant or not at certain confidence levels. For instance, x3x would give us the range within which the parameter mean value is expected to vary with 99.73% confidence. Important standard errors generally used in case of large samples have been stated and applied in the context of real-life problems in the pages that follow. The sampling theory for large samples is not applicable in small samples because when samples are small, we cannot assume that the sampling distribution is approximately normal. As such, we require a new technique for handling small samples, particularly when population parameters are unknown. Surveillance. Gossett, pen name student, developed a significance test known as student's t-test based on t-distribution and through it made significant contribution in the theory of sampling applicable in case of small samples. Student's t-test is used when two conditions are fulfilled with the sample size is 30 or less and the population variance is not known. While using t-test, we assume that The population from which sample has been taken is normal or approximately normal. Sample is A. Random sample observations are independent. There is no measurement error, and that in the case of two samples when equality of the two population means is to be tested, we assume that the population variances are equal. For applying t-test, we work out the value of test statistic, i.e. t, and then compare with the table value of t based on t distribution at certain level of significance for given degrees of freedom. If the calculated value of t is either equal to or exceeds the table value, we infer that the difference is significant, but if calculated value of t is less than the concerning table value of t, the difference is not treated as significant. The following formulae are commonly used to calculate the t-value, I, to test the significance of the mean of a random sample, where x is equal to mean of the sample, is equal to mean of the universe population, x is equal to standard error of mean worked out as under, and the degrees of freedom is equal to n1. The z-test may as well be applied in case of small sample provided we are given the variance of the population. 2. To test the difference between the means of two samples. __. Where x1 is equal to mean of sample 1, x2 is equal to mean of sample 2. x1, x2 is equal to standard error of difference between two sample means worked out as. 3. To test the significance of the coefficient of simple correlation. T equals to, where R is equal to the coefficient of simple correlation and the DF is equal to N2. 4. To test the significance of the coefficient of partial correlation. T equals to, where Rp is any partial coefficient of correlation and the DF is equal to Nk, n being the number of pairs of observations and k being the number of variables involved. To test the difference in case of paired or correlated samples data, in which case t-test is often described as difference test. T equals to, hypothesized mean difference, d, is taken as 0, 0, d is equal to mean of the differences of correlated sample items, d is equal to standard deviation of differences worked out as under. D __. D is equal to differences, i.e., d is equal to xi. N is equal to number of pairs into samples and the DF is equal to N1. Sandler's A-test. Joseph Sandler has developed an alternate approach based on a simplification of t-test. His approach is described as Sandler's A-test that serves the same purpose as is accomplished by t-test relating to paired data. Researchers can as well use A-test when correlated samples are employed and hypothesized mean difference is taken as 0, i.e., H0, D0. Psychologists generally use this test in case of two groups that are matched with respect to some extraneous variables. While using A-test, we work out a statistic that yields exactly the same results as students' t-test. A statistic is found as follows: the sum of squares of the differences A, the squares of the sum of the differences. The number of degrees of freedom, DF, in A-test is the same as with students' t-test, i.e., DF is equal to N1, N being equal to the number of pairs. The critical value of A at a given level of significance for given DF can be obtained from the table of a statistic given in appendix at the end of the book. One has to compare the computed value of A with its corresponding table value for drawing inference concerning acceptance or rejection of null hypothesis. if the calculated value of A is equal to or less than the table value, in that case a statistic is considered significant whereupon we reject H0 and accept Ha. But if the calculated value of A is more than its table value, then a statistic is taken as insignificant and accordingly we accept H0. This is so because the two test statistics with T and A are inversely related. We can write these two statistics in terms of one another in this way. A in terms of T can be expressed as A equals to 2T in terms of A can be expressed as. Computational work concerning a statistic is relatively simple. As such, the use of a statistic result in considerable saving of time and labor, especially when matched groups are to be compared with respect to a large number of variables. Accordingly, researchers may replace students' t-test by Sandler's a-test whenever correlated sets of scores are employed. Sandler's a-statistic can as well be used in the one sample case as a direct substitute for the student t-ratio. For this is so because Sandler's A is an algebraically equivalent to the student's T. When we use a-test in one sample case, the following steps are involved. I subtract the hypothesized mean of the population, H, from each individual score, she, 2. Obtain D and then work out D. I, 2, square each D and then obtain the sum of such squares i.e. D2. 3. Find a statistic as under. A equals to. 4. Read the table of a statistic for n1 degrees of freedom at a given level of significance using one-tailed or two-tailed values depending upon Ha to find the critical value of A. We, finally, draw the inference as under. When calculated value of A is equal to or less than the table value, then reject H0 or accept Ha. But when computed A is greater than its table value, then accept H0. The practical application use of a statistic in one sample case can be seen from illustration number 5 of chapter 9 of this book itself. Concept of standard error. The standard deviation of sampling distribution of a statistic is known as its standard error, S.E, and is considered the key to sampling theory. The utility of the concept of standard error in statistical induction arises on account of the following reasons. 1. The standard error helps in testing whether the difference between observed and expected frequencies could arise due to chance. The criterion usually adopted is that if a difference I less than 3 times the SE, the difference is supposed to exist as a matter of chance, and if the difference is equal to or more than 3 times the SE, chance fails to account for it, and we conclude the difference as significant difference. This criterion is based on the fact that at x3, SE, the normal curve covers an area of 99.73%. Sometimes the criterion of 2SE is also used in place of 3SE. Thus, the standard error is an important measure in significance tests or in examining hypotheses. If the estimated parameter differs from the calculated statistic by more than 1.96 times the SE, the difference is taken as significant at 5% level of significance. This, in other words, means that the difference is outside the limit C.E, it lies in the 5% area, 2.5% on both sides, outside the 95% area of the sampling distribution. Hence, we can say with 95% confidence that the said difference is not due to fluctuations of sampling. In such a situation, our hypothesis that there is no difference is rejected at 5% level of significance. But if the difference is less than 1.96 times the SE, then it is considered not significant at 5% level, and we can say with 95% confidence that it is because of the fluctuations of sampling. In such a situation, our null hypothesis stands true. 1.96 is the critical value at 5% level. The product of the critical value at a certain level of significance and the SE is often described as sampling error at that particular level of significance. We can test the difference at certain other levels of significance as well depending upon our requirement. The following table gives some idea about the criteria at various levels for judging the significance of the difference between observed and expected values. Table 8.1 Criteria for judging significance at various important levels. Pause the video to look at the table. Is equal to standard error. 2. The standard error gives an idea about the reliability and precision of a sample. The smaller the SE, the greater the uniformity of sampling distribution and hence, greater is the reliability of sample. Conversely, the greater the SE, the greater the difference between observed and expected frequencies. In such a situation, the unreliability of the sample is greater. The size of SE depends upon the sample size to a great extent and it varies inversely with the size of the sample. If double reliability is required, i.e., reducing SE to a half of its existing magnitude, the sample size should be increased fourfold. 3. The standard error enables us to specify the limits within which the parameters of the population are expected to lie with a specified degree of confidence. Such an interval is usually known as confidence interval. The following table gives the percentage of samples having their mean values within a range of population mean SE. Table 8.2. Pause the video to look at the table. Important formulae for computing the standard errors concerning various measures based on samples are as under. A. In case of sampling of attributes. I. Standard error of number of successes is equal to where n is equal to number of events in each sample. P is equal to probability of success in each event. Q is equal to probability of failure in each event. NPQ N X 2. Standard error of proportion of successes. 3. Standard error of the difference between proportions of two samples. Underscore where P is equal to best estimate of proportion in the population and is worked out as under P equals to Q is equal to 1, Pn1 is equal to number of events in sample 1, N2 is equal to number of events in sample 2. Note, instead of the above formula, we use the following formula. When samples are drawn from two heterogeneous populations, where we cannot have the best estimate of proportion in the universe on the basis of given sample data. Such a situation often arises in study of association of attributes. B. In case of sampling of variables, large samples, I. Standard error of mean when population standard deviation is known. Underscore where P is equal to standard deviation of population, N is equal to number of items in the sample. Note, this formula is used even when N is 30 or less. 2. Standard error of mean when population standard deviation is unknown, as X where S is equal to standard deviation of the sample and is worked out as under sigma equals to N is equal to number of items in the sample. 3. Standard error of standard deviation when population standard deviation is known. 4. Standard error of standard deviation when population standard deviation is unknown. Where n is equal to number of items in the sample. V. Standard error of the coefficient of simple correlation. Sigma r equals to. Where r is equal to coefficient of simple correlation, n is equal to number of items in the sample. 6. Standard error of difference between means of two samples, A, when two samples are drawn from the same population. Underscore. If P is not known, sample standard deviation for combined samples, S. 1 second may be substituted. B. When two samples are drawn from different populations. Underscore. If P and P are not known, then in their places S and S respectively may 1 to 1 to be substituted. C. In case of sampling of variables, small samples. SP. S. I. Standard error of mean when P is unknown. Pause the video to look at this formula. Note 1. All these formulae apply in case of infinite population. But in case of finite population where sampling is done without replacement and the sample is more than 5% of the population, we must as well use the finite population multiplier in our standard error formulae. For instance, S.E.X in case of finite population will be as under. SEX bar equals to underscore. It may be remembered that in cases in which the population is very large in relation to the size of the sample, the finite population multiplier is close to 1 and has little effect on the calculation of SE. As such, when sampling fraction is less than 0.5, the finite population multiplier is generally not used. 2. The use of all the above stated formulae has been explained and illustrated in context of testing of hypotheses in chapters that follow. Sigma x bar equals to 2. Standard error of difference between two sample means when P is unknown. Sigma x1 bar minus sigma x2 bar equals to estimation. In most statistical research studies, population parameters are usually unknown and have to be estimated from a sample. As such, the methods for estimating the population parameters assume an important role in statistical analysis. The random variables, such as x and 2, used to estimate population parameters, such as and 2 are conventionally called as estimators, while specific values of thus, such as x 105 or to 21.44, are referred to as estimates of the population parameters. The estimate of a population parameter may be one single value or it could be a range of values. In the former case, it is referred as point estimate, whereas in the latter case it is termed as interval estimate. The researcher usually makes these two types of estimates through sampling analysis. While making estimates of population parameters, the researcher can give only the best point estimate, or else he shall have to speak in terms of intervals and probabilities, for he can never estimate with certainty the exact values of population parameters. Accordingly, he must know the various properties of a good estimator so that he can select appropriate estimators for his study. He must know that a good estimator possesses following properties. I. An estimator should on the average be equal to the value of the parameter being estimated. This is popularly known as the property of unbiasedness. An estimator is said to be unbiased if the expected value of the estimator is equal to the parameter being estimated. The sample mean, X, is the most widely used estimator because of the fact that it provides an unbiased estimate of the population mean. 2. An estimator should have a relatively small variance. This means that the most efficient estimator among a group of unbiased estimators is one which has the smallest variance. This property is technically described as the property of efficiency. 3. An estimator should use as much as possible the information available from the sample. This property is known as the property of sufficiency. 4. An estimator should approach the value of population parameter as the sample size becomes larger and larger. This property is referred to as the property of consistency. Keeping in view the above stated properties, the researcher must select appropriate estimator, S, for his study. We may now explain the methods which will enable us to estimate with reasonable accuracy the population mean and the population proportion, the two widely used concepts. Estimating the population mean. So far as the point estimate is concerned, the sample mean X is the best estimator of the population mean and its sampling distribution, so long as the sample is sufficiently large, approximates the normal distribution. If we know the sampling distribution of X, we can make statements about any estimate that we may make from the sampling information. Assume that we take a sample of 36 students and find that the sample yields an arithmetic mean of 6.2, i.e., X 6.2. Replace these student names on the population list and draw another sample of 36 randomly, and let us assume that we get a mean of 7.5 this time. Similarly, a third sample may yield a mean of 6.9, fourth a mean of 6.7, and so on. We go on drawing such samples till we accumulate a large number of means of samples of 36. Each such sample mean is a separate point estimate of the population mean. When such means are presented in the form of a distribution, the distribution happens to be quite close to normal. This is a characteristic of a distribution of sample means and also of other sample statistics. Even if the population is not normal, the sample means drawn from that population are dispersed around. The parameter in a distribution that is generally close to normal, the mean of the distribution of sample means is equal to the population mean. 5 This is true in case of large samples as per the dictates of the central limit theorem. The relationship between a population distribution and a distribution of sample mean is critical for drawing inferences about parameters. The relationship between the dispersion of a population distribution and that of the sample mean can be stated as under: sigma x bar equals to, where x is equal to standard error of mean of a given sample size. P is equal to standard deviation of the population. N is equal to size of the sample. How to find P when we have the sample data only for our analysis? The answer is that we must use some best estimate of P, and the best estimate can be the standard deviation of the sample, S. Thus, the standard error of mean can be worked out as under: sigma x bar equals to, where with the help of this, one may give interval estimates about the parameter in probabilistic terms, utilizing the fundamental characteristics of the normal distribution. Suppose we take one sample of 36 items and work out its mean, x, to be equal to 6.20 and its standard deviation S to be equal to 3.8, then the best point estimate of population mean is 6.20. The standard error of mean X would be 3.836, 3.860, 0.663. If we take the interval estimate of to be X 1.96, X or 6.20, 1.24 or from 4.96 to 7.44, it means that there is a 95% chance that the population mean is within 4.96 to 7.44 interval. In other words, this means that if we were to take a complete census of all items in the population, the chances are 95 to 5 that we would find the population mean lies between 4.96 to 7.44. In case we desire to have an estimate that will hold for a much smaller range, then we must either accept a smaller degree of confidence in the results or take a sample large enough to provide this smaller interval with adequate confidence levels. Usually we think of increasing the sample size till we can secure the desired interval estimate and the degree of confidence. PQN. Estimating population proportion. So far as the point estimate is concerned, the sample proportion, P, of units that have a particular characteristic is the best estimator of the population proportion, P, and its sampling distribution, so long as the sample is sufficiently large, approximates the normal distribution. Thus, if we take a random sample of 50 items and find that 10% of these are defective, i.e., P is equal to 0.10, we can use this sample proportion, P is equal to 0.10, as best estimator of the population proportion, P 0.10. In case we want to construct confidence interval to estimate a population proportion, we should use the binomial distribution with the mean of population, NP, where N is equal to number of trials, P is equal to probability of a success in any of the trials and population standard deviation. As the sample size increases, the binomial distribution approaches normal distribution, which we can use for our purpose of estimating a population proportion. The mean of the sampling distribution of the proportion of successes, P, is taken as equal to P and the standard deviation for the proportion of successes, also known as the standard error of proportion, is taken as equal to. But when population proportion is unknown, then we can estimate the population parameters by substituting the corresponding sample statistics P and Q in the formula for the standard error of proportion to obtain the estimated standard error of the proportion as shown below. P. Using the above estimated standard error of proportion, we can work out the confidence interval for population proportion thus. PZ, where P is equal to sample proportion of successes, Q is equal to 1, P, N is equal to number of trials, size of the sample, Z is equal to standard variate for given confidence level, as per normal curve area table. NPQ, PQN, PQN. We now illustrate the use of this formula by an example. Sample size and its determination. In sampling analysis, most ticklish question is, what should be the size of the sample or how large or small should be N? If the sample size, N, is too small, it may not serve to achieve the objectives, and if it is too large, we may incur huge cost and waste resources. As a general rule, one can say that the sample must be of an optimum size, i.e., it should neither be excessively large nor too small. Technically, the sample size should be large enough to give a confidence interval of desired width, and as such the size of the sample must be chosen by some logical process before sample is taken from the universe. Size of the sample should be determined by a researcher keeping in view the following points. I. Nature of universe. Universe may be either homogeneous or heterogeneous in nature. If the items of the universe are homogeneous, a small sample can serve the purpose. But if the items are heterogeneous, a large sample would be required. Technically, this can be termed as the dispersion factor. 2. Number of classes proposed. If many class groups, groups and subgroups are to be formed, a large sample would be required because a small sample might not be able to give a reasonable number of items in each class group. 3. Nature of study. If items are to be intensively and continuously studied, the sample should be small. For a general survey, the size of the sample should be large, but a small sample is considered appropriate in technical surveys. 4. Type of sampling. Sampling technique plays an important part in determining the size of the sample. A small random sample is apt to be much superior to a larger but badly selected sample. V. Standard of accuracy and acceptable confidence level. If the standard of accuracy or the level of precision is to be kept high, we shall require relatively larger sample. For doubling the accuracy for a fixed significance level, the sample size has to be increased fourfold. 6. Availability of finance. In practice, size of the sample depends upon the amount of money available for the study purposes. This factor should be kept in view while determining the size of sample, for large samples result in increasing the cost of sampling estimates. 7. Other considerations. Nature of units, size of the population, size of questionnaire, availability of trained investigators, the conditions under which the sample is being conducted, the time available for completion of the study are a few other considerations to which a researcher must pay attention while selecting the size of the sample. There are two alternative approaches for determining the size of the sample. The first approach is to specify the precision of estimation desired and then to determine the sample size necessary to ensure it, and the second approach uses Bayesian statistics to weigh the cost of additional information against the expected value of the additional information. 7. The first approach is capable of giving a mathematical solution, and as such is a frequently used technique of determining n. The limitation of this technique is that it does not analyze the cost of gathering information vis-a-vis the expected value of information. The second approach is theoretically optimal, but it is seldom used because of the difficulty involved in measuring the value of information. Hence, we shall mainly concentrate here on the first approach. Determination of sample size through the approach based on precision rate and confidence level. To begin with, it can be stated that whenever a sample study is made, there arises some sampling error which can be controlled by selecting a sample of adequate size. Researcher will have to specify the precision that he wants in respect of his estimates concerning the population parameters. For instance, a researcher may like to estimate the mean of the universe within 3 of the true mean with 95% confidence. In this case, we will say that the desired precision is 3, i.e., if the sample mean is 100 rupees, the true value of the mean will be no less than 97 rupees and no more than 103 rupees. In other words, all this means that the acceptable error, E, is equal to 3. Keeping this in view, we can now explain the determination of sample size so that specified precision is ensured. A. Sample size. When estimating a mean, the confidence interval for the universe mean is given by __, where x is equal to sample mean. Z is equal to the value of the standard variate at a given confidence level to be read from the table giving the areas under normal curve as shown in appendix, and it is 1.96 for a 95% confidence level. N is equal to size of the sample. P is equal to standard deviation of the population, to be estimated from past experience or on the basis of a trial sample. Suppose we have P 4.8 for our purpose. If the difference between and X or the acceptable error is to be kept within 3 of the sample mean with 95% confidence, then we can express the acceptable error E as equal to E equals to N equals to. In a general way, if we want to estimate in a population with standard deviation P with an error no greater than E by calculating a confidence interval with confidence corresponding to Z, the necessary sample size, N, equals as under. N equals to all theses applicable where the population happens to be infinite. Bu in case of finite population, the above stated formula for determining sample size will become N equals to underscore determination of sample size through the approach based on Bayesian statistics. This approach of determining N utilizes Bayesian statistics and as such is known as Bayesian approach. The procedure for finding the optimal value of N or size of sample under this approach is as under. I. Find the expected value of the sample information, EVSI, for every possible N. 2. Also work out reasonably approximated cost of taking a sample of every possible N. 3. Compare the EVSI and the cost of the sample for every possible N. In other words, work out the expected net gain, N, for every possible N as stated below, for a given sample size, N, EVSI, cost of sample, is equal to, N, 4, form, 3, above the optimal sample size, that value of N which maximizes the difference between the EVSI and the cost of the sample, can be determined. The computation of EVSI for every possible N and then comparing the same with the respective cost is often a very cumbersome task and is generally feasible with mechanized or computer help. Hence, this approach, although being theoretically optimal, is rarely used in practice.